Today we're going to get some practice using the fundamental theorem of calculus together with u-substitution. And this is really going to be nothing different than what we were doing last time, because last time what we said, okay, find an antiderivative and then plug our numbers in and subtract. Well, sometimes finding the antiderivative might involve something like u-substitution. And in that case, the only step where you're doing something like different than what we did last time is that u-substitution step, but that's just finding the antiderivative. So let's kind of jump in. There's one subtlety that we have to just be kind of a little bit careful about in terms of notation, and I'll point that out along the way. So if we look at this problem here, I want you to be careful that this is cosine of x times cosine of pi sine of x. The pi sine of x lives inside of that second cosine. And so what I would suggest here is, since we have a function inside of a function, the pi sine of x is inside of cosine, I'd probably try u substitution here. In that case, I would pick u to be pi sine of x. My du over dx then is pi cosine of x. And if I solve, multiply both sides by dx and then divide everything by pi cosine of x, I'll get something like this. So if I rewrite my integral, I'm going to save the bounds for just a second. I'm going to get cosine of x times cosine of u times du over pi cosine x. Okay, this is a definite integral. It has bounds on it, so I need to include my bounds. The problem right now is that I have just rewritten the integral in terms of u. The cosine x's cancel out. So my bounds should really be u values. But the way that I can work around this is I can say that 0 and pi are x values. So I can say, make sure that I'm indicating that these are x values, not u values, because they started out as x values, okay? If you read certain textbooks, most textbooks will convert these to values that are u. I think that step is a little bit hard for students to do usually. So I'm just gonna keep reminding ourselves that the 0 and pi are x values. We should only plug them in for x, never plug them in for u, okay? And so now we just have to anti-differentiate still. So let's simplify. We can pull the 1 over pi out front. So I'm going to still keep writing this as x is 0 to x is pi. You really need to do that if you don't write the x is equal to at this stage. If you just write 0 to pi, then I'll take points off, because what you would be saying there without indicating what variable these are, you would be telling me that you think these are u values, not x values. Okay, since the rest of your integral is in terms of u. Okay, so antiderivative of cosine is sine. So we're going to get sine of u, 1 over pi, from x is 0 to x is pi. Now let's replace everything with x. So we're going to have sine, sine replace u was pi sine of x. Whoops. And from x equals 0 to x equals pi. If you don't write the x now, that would be okay, because now we're back in terms of x. But the thing that we're being very careful about is you should not plug these numbers in at this point. So don't do that, because the variable inside sine is u at this point, not x. So we should only plug the 0 and pi in for x's. Okay, so we can plug 0 and pi in now. So we plug in the pi first. So we're going to have sine of pi sine of pi, which seems like it's going to be really messy, but it'll be okay. Minus 1 over pi sine of pi sine of 0. Okay, so let's do this. Sine of pi is 0. So this whole inside will be 0. So we're going to be left with 1 over pi sine of 0 minus 1 over pi sine of 0 is 0. So we're going to get 0 on side as well. So this is sine of 0 is 0. So everything's going to be 0 here. Okay, this one's interesting. If you look at the graph of this, what we'll notice is that areas are canceling out. So let me show you that. So when we look at the graph of this function, this is what that function looks like. To me, it looks like a little like dance or something. I don't know. It's a funny little dance. So let me restrict ourselves to 0 to pi. Yeah, that's what we were doing. So what we've got is kind of this like funky little graph here. What we are going to find out next week is how does an indefinite, or how does a definite integral deal with like area when there's things under the x-axis? What it's going to turn out is that the definite integral counts anything above the x-axis as positive, and then anything below the x-axis as negative. And so what we're going to see here is that like this area and this area are the same, so those two cancel each other out. This area and this area are the same, so they cancel each other out as well. And that's why we're getting 0 for the integral here. So whenever we have a region where the area above the x-axis is the same as the area below the x-axis, that definite integral will give us 0 out. So that's just kind of a fun little fact that I want us to think about as we move forward, but we're going to focus on that in a couple of days when we talk about net area. So it looks like this next problem is asking us to find the area under a graph. And so we need to look at this graph and make sure that this region we're looking at is actually positive. Otherwise, an integral won't tell us something. So let me pull Desmos back up here and we will see what this graph looks like. So let's see, here is hopefully, well, there we go. Here is this graph that we're looking at. And we are looking at it on the interval from 2 to 4. So this looks to be 2, 3, 4. So it's this region here that we're looking for the area of. That region is totally positive. So the indefinite integral will be giving us that area under the curve. So we can just find this integral from 2 to 4 of that function. And while I bring my other screen back up, why don't you guys start practicing that and see how far you can get in the amount of time it takes me to pull my screen back up. And hopefully we're going to be using a u-substitution here. Here it comes. Okay, so I'm not going to actually graph this one, but we should be looking at the integral from 2 to 4 of 4 ln of x quantity squared over x dx. I see that a u-substitution is probably going to be good here. The thing that's inside of another function is the natural log, so I'm going to pick ln of x to be my u. My du over dx then is 1 over x. When I cross multiply here, I'm going to get x du is equal to dx. And so if I rewrite my integral, I'm going to remind myself that my 2 and my 4 are x values, and not just myself, but when I write this down on my paper, I'm reminding the whole world that I know that these are x values, not u values. So I've got the 4. I'm going to have u squared over x times x du. The x's cancel out. So we're going to be left with 4u squared. Don't forget our bounds. We just have to keep writing them. Du. So this is going to become 4/3 u cubed. From x is 2 to x is 4. We replace our u with ln of x. So we're going to have 4/3 ln of x cubed from 2 to 4. Remember, I don't have to write my x's anymore at this stage because everything is in terms of x, but you can still write x is equal to 2 and x equals 4 if you want to remind yourselves. So now I'll plug in the 4, so I get 4/3 ln of 4 cubed, and I'll plug in the 2 minus 4/3 ln of 2 cubed. That's not going to be a pretty number, but when you type it into your calculator, you get 3.108 is the area of that region.